Hello class, and welcome to today's algebra lesson, which is about representing relations. By the end of today's lesson, you will be able to represent relations in different formats, interpret the graphs of relations, and choose and interpret the appropriate scales for the axis and origin of graphs. So we're going to start with some vocab here. A relation is a set of ordered pairs. So anything listed out as coordinates that could be put on a graph is a relation. They may form a particular pattern, they may not. It's just a list of coordinates that we have on the in order to be a relation. The x coordinates, when we pull those out separately, we call those the domain. That is what we refer to as the inputs of any particular relation. So the domain is the inputs. That's what we start with. The y values then, the outputs, are what we call the range. This is the result of whatever we have in the problem. Whether there's a specific formula and pattern to get there or whether it's random will depend on what kind of relation we have. But the domain, the x's are the inputs, and the outputs or the y's are the range. A mapping is a visual illustration of how each element in the domain is paired up with an element in the range. So it's a visual way to look at how we get from our inputs to our outputs. So there are four main representations that we have of a relation. The first is simply the list of ordered pairs. That's what you are going to see most frequently to start the problem, is just the list of the ordered pairs. The next piece, which you are familiar with, is the table. This is where we split our x and y values into their own parts. When you are making a table, the x values need to be in order from least to greatest. So in this case, when I go through and look at my numbers, my smallest x value is -2. Then I have -1. Then I have 1, 4, and 5. Within the table now, I need to match up the range or those y values with their domain values. So the -2, the y, the output, is -2. -1, the output is 5. 1, the output is 2. 4, 5. And then 5, -2. So each x is paired with its exact y in the table. Again, you are probably familiar with how we graph things, so that's going to be our next representation. So I'm going to go ahead and put the first one is 1, 2, put a dot at 1 to the right and 2 up. Then we've got 4, 5, which is 4 to the right and 5 up. Then we've got 5, -2, which is 5 to the right and 2 down. Then we've got -1, 5, which is 1 to the left and 5 up. And then we've got -2, -2, which is 2 to the left and 2 down. So our graphing is just what we have done previously in the coordinate plane, which is just put our points on based on left, right, and up, down. The last piece, the new piece, is the mapping. When we do the mapping, you want to, again, have your domain and your range, so your inputs and your outputs. When we list either the domain or the range, if there is any repeats, we only list them once. So if I go back to my x's, none of my x's repeat, and those were already from least to greatest. So the x column for this particular one does not change because there was no repeated x values in my domain. The range now needs to get rearranged to also be from least to greatest. So I'm looking at my y's, and my smallest number is -2. Even though it is listed twice, I'm only going to list it once when I'm creating my map. Then I have 2 and +5. So I take all of my possible y's and list those in order. Then the point of the map is to connect the dots from the x's, the domain, to the range, the y's. So my first one negative 2x goes with negative 2y. My next one, negative 1x, goes with 5y. My next one, 1x, goes with 2 for y. 4 for x goes with 5 for y. And then 5 for x goes with negative 2 for y. So we connect our dots using arrows to show which numbers actually belong together. Again, the key difference between the map and the table is in the table, the x's have to be in order and every pair is shown individually. With the map, the x's and the y's have to be in order and each number can only be listed once. Go ahead and try this one on your own, creating the table, the graph, and the map. So we go least to greatest in our table, we have our graph, and then our map with, in this case, 8 having 3 different outputs that it is going to. The next piece when we're talking about function is the independent and dependent variable. Again, these are another pair of synonyms for domain and range, or x and y. The independent variable is your inputs, and that's what decides the outcome, determines your outputs. So that's our domain. The dependent variable then, those are the results or the outputs of a relation. Those are the y values or the range values. So these are synonyms for domain and range. When we're talking about independent and dependent variables, it generally means we want to decide what is causing the other thing to happen. So, for example, the average temperatures in Minnesota decrease from August to December. Determine the independent variable. So we are looking at the months and the temperatures. We want to decide if the temperature determines the month or if the month determines the temperature. If we are thinking about the weather here in Minnesota, we know that as the months go on, our weather here gets colder. So our independent variable in this case is going to be the months from August to December, because that's the portion of the year that this problem is talking about. Our dependent variable then, the result of the changing months, is the changing temperatures. So our dependent variable is going to be the average temperature. So if you were going to put this on a graph, your x-axis would be labeled August, September, October, November, December. And then your dependent, your y-axis, would be labeled with the different possible temperatures that you could encounter during those months. Go ahead and try this one on your own to determine the independent and dependent variables. In this case, the independent variable is time. The change in time is causing the ticket prices to change, so our ticket prices are our dependent variables. So the next thing we want to be able to do is put a little bit more verbalization to this independent-dependent variable relation. So we want to be able to describe different portions of a graph as we look at it. So we're going to start as you move from left to right on the graph, our time value is going to be increasing. We know when we're on a number line, moving to the right, we are increasing. So as we're going to the right, our time is increasing. Our distance, as we look at this first chunk, is also increasing. So as we start this graph, both values are increasing until the graph becomes stationary, or what we are going to call a flat line. So that flat line, that stationary piece, means that time is still increasing. We are still moving from left to right on our graph, but the distance now is constant. So the distance is not changing. So that means the writer is stopped. They stopped moving, they took a pause, they took a break. Whatever you need to say here to indicate that the rider is not moving. Then, as we look at the last piece, the rider continues moving forward. So they continue their distance. So we want to be able to look at the different segments of the graph and determine what's happening. Go ahead and try this one on your own, filling in these different blanks with words that would appropriately describe the graph. As you are looking at this problem and going in and filling out the words you use do not have to be verbatim exactly what I am saying, but they should at least be synonyms. So the first part is our time is increasing and our text messages are also increasing. Then we get to one of those flat lines, which means you have stopped sending text messages and sent 0 messages during this time window. After that, you continue to send text until you stop again, you reach another flat line, and then you start sending messages again. So looking at those different up, flat line, and then up again. The last piece we are looking at here is how we can scale different graphs. So a scale tells you what you're counting by as you are looking at the domain and range or the x and y axis. One key thing that students often confuse is the scale on your x-axis does not need to match the scale on your y-axis. So if you are able to count by ones going across, but your range values are significantly larger than 1, you can count by something other than ones as you move vertically on that y-axis. So, we're going to start by looking at this particular relation and choose an appropriate scale and then graph the points. When you are doing this, the first thing you're going to want to look at is your domain. So we're going to look at the x's and we're going to say the lowest point, which I've got 5, negative 36, 25, negative 10, and 1. So my lowest point is negative 36 to my highest point, which is going to be 25. So then I want to look, and I'm going to say, so that's about negative 40 to 25. To make sure we include all of the possible values that we could have. So if I'm going from negative 40 to positive 25, I can go ahead and count then by 5s on that x-axis. So I can go across by going by 5s and make it to negative 40 and positive 25. So everything is going to fit. Then I'm going to repeat that same process with my y's. So for my y values, my smallest y could either be 80, 48, negative 91, negative 50, or positive 22. So the smallest one being negative 91, 2, and then our biggest value in this case being 80. So when we're looking at these ones, I need to be able to get from negative 91 all the way up to 80. So when I'm looking at the about piece, I'm going to drop that down to negative 95 to make sure the 91 is included all the way up to 80. Then, if I've got to get from negative 95 all the way up to 80, I'm going to go ahead and count by 10s on the y-axis. Gives me a little bit more leeway to be able to get from 90 to 80, but isn't too big that we're only taking up a very small chunk of the graph. So then our last piece is to actually graph those points. So I start at 580, so I go 5, and then I go 10, 20, 30, 40, 50, 60, 70, 80. So my first point is at 580. Then I need to go negative 36, 48. So negative 5, 10, 15, 20, 25, 30, 35, 36 is a little bit past. And then we go 10, 20, 40, 10, 20, 30, 40, and then up to 48. So my next point is going to be approximately right there. Then I've got a positive 5, 10, 15, 20, 25, and a negative 10, 20, 30, 40, 50, 60, 70, 80, 90, and a little bit past to get me to negative 91. Then I have negative 5, 10, negative 10, 20, 30, 40, 50. So that one's a nice even coordinate that we can dot right on the intersection of the lines. And then my last one, I've got 1, 22. So I go over just one space, which is only part of the way over, and then 10, 22. So we've got, when we're doing these choosing a scale, there's often going to be dots in between the actual intersections. You probably won't land on the lines very often, but it does happen sometimes. Go ahead and choose an appropriate scale for the x values. So we're going basically from negative 10 to 35, which would give us an appropriate scale of 5. Now go ahead and try the y values. So we are going from negative 55 to positive 82, which is going to round us from negative 55 all the way up to, that should actually be 85 to make sure we include all of our values. So we're going to go ahead and count by tens, and then we end up with the graph as you see to the right. The other piece with choosing the scale is going to be to look at the origin. So when we're trying to determine the origin, remember that the origin is where the graph starts, so it originally should be at 0, 0. However, when we look at this table, our x values, our years, are up in the 2000s. So it wouldn't make sense for us to start at 0 and try to count all the way up to 2000. So that means I can change what my origin is. We're going to change the starting point, and in this case, I'm going to say the starting x value should be at 2,500, or the year 2005. Then we have our y values, which is the total snowfall in inches, and I'm looking down for the smallest value, and my smallest value is 1. So I want to make sure I'm still starting at 0 for this one, because I need to start at 0 and then move up in terms of my total snowfall. Then I need to figure out the scale. What is appropriate for us to count by as we are moving along the graph? So when we look at this, I'm going to say x, and then we're going to say 1 scale mark. So that would mean 1 space on the graph for my x's. If I look at the x's, the years are consistently in a row. So I can say 1 scale mark equals 1 year. I don't have to change the scale on that because every year follows in a row. For the y's, I'm going to say that 1 scale mark again to say 1 space on the graph. But now I need to be able to get from 1 all the way up to 43. And I want to be able to count by something that's going to make my graph a little bit more manageable. So I would say that it would be fair to say 1 scale mark here is going to equal 5 inches of snow, because we want to be able to fit, again, everything, and counting by ones from 0 all the way up to 43 is going to take up a lot of space. Go ahead and try this one on your own, determining both what the origin should be and what the scale for each axis should be. So as we look at our origin, again, we're starting in the year 2001, so we don't want to jump all the way from 0 to 2001. By changing the scale, So we're going to have that change of origin. We're going to have it start at 2001. Then I need to look at my Y values, aka the coins produced. And we get down fairly low there, down to 3.5. So I'm going to start that one at 0. Then we have to look at the scale. Again, one scale mark can equal 1 year here because all of the years are following in order, one after the other. And then I need a way for my Y's to get from about 4 to about 20. So one way to do that would be to go by 2s. If you said you were going to count by 4s, that would also be acceptable. Even 5 would work as a scale for this graph. So the last thing we're going to look at here is interpreting scales and origins that have been picked for us. So, based for this problem, the average number of posts per day on a social media site each year is given in the table. Interpret the meaning of the axis, the scales, and the origin of the corresponding graph of the data. So when I do this, I want to start at the x-axis. So when I'm looking at the x-axis, I have 0, 1, 2, 3, 4, 5, all the way up to 10. I need to figure out how these values of 1 through 10 relate to my years. So I like to pick out a point that I know for sure, which in this case is at 100. 100 as a Y value output is shown here in the table. So that means the year 2012 has to be year number 4. So then I can go ahead and backtrack and decide that year 0 is 2008. So what that means is the y-axis represents the years since 2008, because 2008 became our new point of origin since it's not appropriate to start at year 0. Now looking at the y-axis, we're going up 50, 100, 150, so we're counting by 50s here. And this would represent our average posts per day in millions. So the Y represents, again, that average posts per day. And you want to make sure you emphasize that that is in millions. So it's not just when I look at the graph that in 2008 there was 15 posts. It means in 2008, there was 15 million posts. So we want to make sure we include that million value there. Now on to looking at the scales. On the x-axis, we are increasing by 1. So 1 mark is equal to 1 year. On the y-axis, wrong direction. On the y-axis, we are going up by 50. So that means 1 mark is equal to not just 50, but 50 million posts that are occurring. So that means our origin, our starting point, represents 2008, and in this case, 0 posts per day. Because on our y-axis, we're counting by 50s, and down from 50 would give you that value of 0. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.